Well, it's a very big day. You could argue this is the most important lesson of the entire class. No, I mean the whole year. The topic is the fundamental theorem of calculus. I mean, when a theorem is called fundamental, that means something. So let me just briefly remind you about something that you probably haven't forgotten, but just in case. We say that capital F of X is an antiderivative of little f if the derivative of capital F is little f. It's a function whose derivative is little f. Right? We've seen this before. Antiderivatives, right? So taking the antiderivative of little f would give you big F. Okay, fine. Okay. With that in mind, here's the theorem, the fundamental theorem of calculus, which we abbreviate as FTC. Let capital F be an antiderivative of little f. Then the integral from a to b of little f dx is equal to capital F of b minus capital F of a. That's it. That's the theorem. It's really a theorem of incredible importance because what it tells you is that you can evaluate integrals very easily as long as you can find an antiderivative for the function that you're integrating. Notice that this is an equality sign. It's not approximately equal. It's exactly equal. This allows you to basically do away and forget about all these stupid Riemann sums, as long as you can find an antiderivative. If you can find an antiderivative, there's no need to approximate the integral. You can find its exact value by doing this. Okay? It's not hard to use. And I'm going to give you an example, and that'll really be it. But I want to quickly introduce some notation that will make things a little bit more clean. Just very briefly, notation. Let's say you have something like capital F of X. And then you put a big vertical bar like this. And then you put an A down here at the bottom of the bar and a B up here at the top of the bar. this notation means capital F of B minus capital F of A. This bar is really a notation that you might have seen in your physics class, but it really just means evaluate. It means evaluate this function at this number, so F of B, and then subtract this function evaluated at the bottom number. That's all that it means, okay? So it's just convenient to have. Yeah, okay, let's do an example. Let's find the integral from, let's say, 1 to 2 of the function x squared dx. Okay. And we're going to find it exactly. We're not going to approximate it with a Riemann sum or anything like that. Very quickly, before I do it, let me just remind you what that means. Not that you have to draw any pictures to answer the question, but what this is the area under the graph of x squared from 1 to 2. So it's the area of this region right here. Okay. Technically the signed area, but since it's above the x-axis, regular area, signed area, same thing. Okay, so that's what this thing means. And we're going to find it exactly by using the fundamental theorem. So what does the fundamental theorem say? It says, if you can find an antiderivative, capital F, for your function that you're integrating, little f, then you can use it to evaluate the integral. All right. So basically what you're going to do is try to find an antiderivative for this function. Well, it's pretty easy. What's an antiderivative for x squared? A function whose derivative is x squared. I mean, think first about the exponent. It's got to be x to the power of what? To the 3. Now, if you check, that's not quite right, because if you take the derivative of this thing, you get 3x squared. We don't want 3x squared. We just want x squared. So what do I need to put here? Yeah, put a 1/3 in front of it. Now, when the 3 comes down, it just gets turned into a 1. So that's an antiderivative, right? Good. And the fundamental theorem says what you need to do is take that antiderivative and evaluate it here at the upper limit, and then subtract that same function evaluated here at the lower limit. Using this new vertical bar notation, I could write that succinctly as this function evaluated from 1 to 2. Is that okay? So literally all this means is evaluate this function at 2. So that would be 1/3 times 2 to the 3rd minus this function evaluated at 1. That's 1/3 of 1 to the 3rd. And whatever that number turns out to be, that will be the value of the integral. So 2 cubed is 8. Divided by 3 is 8 cubed. Minus 1/3 times 1 cubed, that's just 1/3. So 7/3. That's it. We don't prove the fundamental theorem in this class. The proof is way beyond what we can do in this class. But you've already seen that integration does have something to do with anti-differentiation in the linear motion problems we did, right? Integrating velocity gives you stuff about position. Whereas taking the derivative of position gives you velocity. So integrating undoes differentiation. So it's some kind of antiderivative thing. That's not a proof, but it's a convincing, argument. Okay. I don't have much else to say. There's just a little bit more that I want to say about notation. And the so-called definite versus the indefinite integral. Okay. So this integral is called the definite integral. So far, the only integrals we've looked at have all been definite integrals. So I'm sure you're wondering what is a not definite integral or an indefinite integral. If I write an integral symbol without any limits of integration, without an a or a b, and I just write the integral symbol, and then I write the function dx, that is what we call the indefinite integral. And I'm sure you're wondering what in the world that means. All it means is the antiderivative of f. That's it. That's what it means. Of course, to be clear, like these two objects are totally different things. The first guy, which we've been working with for several days, the definite integral, that's a number. It's an area under a curve. It's a number. Are you with me? This second thing, being the antiderivative of a function, this guy is a function. So the first thing's a number, the second thing's a function. They're totally different objects. But we use very similar notation for them because, of course, the fundamental theorem says this guy here, the definite integral, can be evaluated using antiderivatives. And so we use the same notation to say antiderivative because the two notions are so closely linked. Integral and antiderivative are very, very closely associated, hence we use similar notation for both of them. But just as an example, if I just wrote integral x squared dx, we did a definite integral for this function a moment ago. This is an indefinite integral because there are no limits of integration. This thing is not an area under a curve. This expression literally just means the antiderivative of x squared. That's all that it means. This is a function, which we sort of already thought about. It's 1/3 x to the third. Are you with me? You might remember, though, that this function has more than one antiderivative. Like if I wrote 1/3 x to the third plus 7, that would also work, right? Or plus 12 or plus any constant. And you might remember that sometimes to represent the fact that you can have the addition of any constant, we write plus c. I want you to do that whenever you evaluate one of these things. Whenever you find an indefinite integral like this, you need to write plus c. It won't be important for a long time. And you'll be like, why am I doing this? This is so stupid. It will eventually become really important. And if you forget it, you'll start getting things wrong. Okay. So that's really all the new stuff that I have to say. I'm just going to do one more example to make a point about something. Guys, you know how to find derivatives for lots of functions. Like you know how to find the derivative of most functions at this point. Not everything, but most. Antiderivatives, you know almost nothing. The only thing really that you guys can reliably find antiderivatives for right now is stuff that is polynomial-ish. Remember when we first started derivatives, the only things that we could really find derivatives for were like polynomial functions, like x squared plus 3x plus 1. That includes other stuff as well, right? Like square roots, but like x to some power, like x to the 1/2 minus x to the -7, stuff like that. That was all we could do. That's where we are with antiderivatives right now. Those are the only things we know how to do. And so if you have a function which doesn't look polynomial-ish, you need to make it look polynomial-ish, just like we did for derivatives way back when. So if I give you something like this, integral square root of x times 1 over x to the 3rd, like minus x or something like this dx. This is an indefinite integral, and of course, it just means find the antiderivative. But that's not really written as a polynomial yet. So you have to rewrite it. So let's just rewrite this expression as a polynomial. Then we can think about what the antiderivative will be. Square root of x, that's x to the 1/2, right? 1 over x to the 3rd, that's really just x to the -3. The x here is already basically fine. Okay, that's getting closer to a polynomial-ish kind of expression, but what else do I have to do to make it truly like a number times x to a power plus a number times x to a power plus, I have to distribute, right? You have to distribute the x to the 1/2. So x to the 1/2 times x to the -3, that's x to the, I think, -5/2. Is that right? When you add those two exponents. And then x to the 1/2 times x to the 1, that's x to the 3/2. Is that okay? Okay, now we're ready to find an antiderivative because it's polynomial-ish, right? So how do you do this? Well, so here's the antiderivative. Start by thinking about the exponent. It's got to be one more than the original, right? Don't be confused. It's negative. You still want to go one more. That would be -3/2, wouldn't it? Are you with me? That would be the appropriate exponent because that exponent is one more than -5/2. But then, of course, you need to put some number in front of this guy because if you take the derivative right now, you'll get a -3/2 in front that you don't want. So you need to put a -2/3 in front. Now, when the exponent comes down, it'll cancel. Is that okay? And then likewise with this guy, minus, what should the exponent be? Yeah, 5/2, right? One more than the original exponent. And now what coefficient do I need to put in front? 2/5. Okay, so that is, well, what have I already forgotten? What am I forgetting? Yeah, the plus c, okay? So that's the indefinite integral, that's the antiderivative. Guys, when you're finding antiderivatives, it's really a good idea to just, in your head, double check that when you take the derivative, you get the right answer. Antiderivatives are a lot harder than derivatives. It's easy to check your answers often, so you should. Any questions on that? Good. Okay. Cool.